So this is the second part of 2.6, and yeah, so let's start with looking back at some of those examples we just did. So there was let's start with let's start with this one. Sorry, here. So f of x was this was a piecewise function. So 1 if x is not 2, and 3 if x is equal to 2. F2, yeah. Okay, so let's look at the graph quickly. Okay, so the graph was like this, right? So we have, this is 1, 2, 3, 1, 2, 3. So there is a hole at 2, so something like this. And then at that, for x equals 2, the function has a value of 3. 1, 2, 3. Okay, so let's check those conditions. Okay, let me try again. Okay, so 1, 2, 3. Okay, so this is 3, and this is 1, and this is 2. Okay, so the first condition was that function needs to be defined, right? So we're checking basically the number c, right? That point of possible discontinuity is that 2, right? So we're checking first whether the function is defined at 2, and it is, right? So f of 2 equals 3. So no problem there. The second condition was that the limit exists, right? So let me write it here. So second condition, so limit with x going to 2, approaching 2 of our function of f of x. I'm not going to write it separately, right? We should maybe write it separately, approaching 2 from the left, approaching 2 from the right. But it's easy to see that the limit, right? If I approach the function from the left, I mean approaching the 2 from the left, the limit is 1, the value of the function is 1, right? And then if I'm going with my axis towards that 2, the value of the function, the limit is 1. Okay, so the limit exists and is equal to 1. Right, so that first condition, right, we're passing. Second condition, fine. But now the third condition was that limit, so limit with x approaching 2 of f of x needs to be the same as f of 2, right, as the value of the function at 2. So unfortunately that doesn't work, right, because the limit is equal to 1 and value of the function at 2 is equal to 3. Okay, so they're not equal, so we're failing that condition. Okay, so yeah, value of the function, right? We have it here. The limit, we have it here, and they need to be the same. So the third condition fails, and the function is discontinuous, and it's a removable discontinuity. Okay. All right, let's look at another example. So there was the first one we looked at, f of x equals 1 over x. All right, so this one, checking for the first condition. So first condition was that the function needs to be defined at c, right? So we were checking, so continues at 0. Is it continues at x equals 0, right? So that was the possible point of discontinuity. So f of 0, well, unfortunately, is undefined, so 1 over 0, undefined. So function is discontinuous, right? So we failed the first condition. Let's look at another example, the last one maybe, or maybe I have one more. Okay, so this is an example with parabola and a straight line. So this was also a piecewise function. So x plus 2 for x is less or equal than 0. Let me write if, right? Sometimes we have that if. X is less or equal than 0, and then x squared plus 2 if x is less than 0, greater than 0. Okay, so graph it. Okay, so blue. So x plus 2. I'm not going to graph it, you know, the way I did it. We've already done it, right? So that's that. This one, y equals x plus 2. And then we had the other one. Let me use maybe yellow. Right, so that's that parabola. And okay, so here it is. Okay, so now let's look at those conditions. Okay, the first one. So we're checking, right, so that c is equal to 0, right? That's the only possible point of discontinuity, right? Because we know that this whole function is continuous, this whole function is continuous, but we have, right, combination of those two. We have a piecewise function. So we're checking at 0. So that number c is 0. So what is f of 0? Is that defined? Is everything fine with that? Let me write it somewhere else. I don't have space here. So this is condition number 1. So we have f of 0. Is the function defined at 0? Well, it is, right? So 0 is part of this function, right? Because of that equal sign here. So I just do 0 plus 2 equals 2. Okay, then the limit. So limit with x approaching 0, right, of f of x. Right, so we can see that the limit is 2. Okay, and then the third condition. So we can simply plug in, right? Plug in that 0, right? We're looking at this condition, this one, right? We have a function, and 0 goes with this function. Plug it in, and we get 2. And also you can see, right, that if I'm going towards 0 with my x's, my y's are going towards from there towards that 2, right? So this is 2 right there. Okay, so now we have the last condition, right? So f of 0, so value of the function at 0 needs to be the same as limit of the function when x approaches 0. And yeah, seems to be working, right? So we had this condition was fine, this condition was fine, and here we have 2 does equal 2. Okay, so I hope you see it, right? So yeah, value of the function, limit 2. Okay. Yeah, one more example. So this one is not something that we've already done. I just want to just show you. And so this is, I have in my notes example 5. I'm not sure if this is correct. Alright, so we need to figure out, discuss the continuity of something, of a function like this. So f of x equals square root of 4 minus x squared. Okay, so this is half a circle, and the graph looks like this. Okay, so this is 2, 2, 2, 2, 2, negative 2, and the graph looks like this, right? So it's part of the perfect circle. Yeah, so in this case, right, we're just going to say, how can we write it? Oh, let's just say the function is not defined. Is not defined outside of it's pouring rain and there are 2 kids outside. Defined outside of interval from negative 2 to 2. And then we say function is continuous, f is continuous in this interval, negative 2 to 2. Okay. All right, so now let me give you a couple of problems to practice. So practice, or let's write problems. Let me look at that. Yeah, it's a little bit too thick. Let's do this. Let's try that. So problems. So discuss continuity. So the first problem is f of x equals, it's a rational function, so x squared minus 1 over x plus 1. And then, right, so you'll have to check at 2 x's, so c equals negative 1. Right, so you need to check. I would like you guys to show work. Right, so checking all those conditions, unless of course you fail, right, and then you don't need to check anymore. And then c equals 1, so that's the first problem. And then the second problem is maybe a little easier. Okay, you can also talk about whether that discontinuity, if something is discontinuous, right? Say whether that discontinuity is removable or not. Okay, so this one is x minus 2, and the c equals 1. Okay, so yes, figured it out, discuss the discontinuity, show work, right? So you need to show like 3 sets of those conditions. Anyway, let me give you the answers. So the second one is discontinuous, and it's non-removable. And now that first one, so that was the answer for the second problem. The first one, okay, I'm trying to, okay, maybe I should, here you go. Yeah, so I can see that problem. Okay, so that's the answer for the second one. And the first one, let me think about this one. So continuous, the function is continuous for c equals 1. And discontinuous for c equals negative 1, and it's removable. Okay. All right, so we have that. Okay, so next thing we'll look at is properties of continuous functions. That's not supposed to be we. Okay, so properties of continuous functions. Okay. Functions. And yeah, we'll look at two different functions. So if f and g are continuous, then yeah, we can do operations on them, and also some difference, etc., will be continuous. So let me finish this. Then f plus g, f minus g, this is supposed to be g. So g, f times g, and f divided by g. So yeah, if we do those operations on functions, so those, right, so product, division, sum, and difference are also continuous. Also composition of functions, right? So composition is also continuous. So f g is also continuous. So let me show you what that means. So let's say f of x is square root of x, right? G of x is x squared minus 4. And if we put them together, right, if we do f of g of x, right, so we're going to get square root of x squared minus 4, right, is also continuous. Continuous, yeah, so this says continuous. I hope you see that. All right. Yeah, a couple more examples, and then we'll do a couple other types of problems, and yeah, we'll be done with this section. Okay, so yeah, let's think about some better, maybe this is example 6, I believe. So let's start with that. And so again, discuss continuity. Let me write it. So discuss continuity. And then the function is tangent. So y equals tangent x. And we've already looked at graph of it. So I'm just going to sketch it. So negative pi over 2, pi over 2, and then 3 pi over 2. Okay, so we have those vertical asymptotes here. So obviously function is going to be discontinuous, but yeah, we need to figure out which what condition it will fail. Okay, so the graph looks like this. Make another branch here and another branch here. Right, so we're checking at those particular axes, right? So negative pi over 2, pi over 2, 3 pi over 2, etc. So you can see that the function is discontinuous. It's obvious. It fails, well, it fails the first condition. So let's maybe write it. So the first one, right? So f of, let's do pi over 2. Right, so we have tangent of pi over 2, right, is undefined. So the conclusion is function is discontinuous. Okay, so maybe take a moment and pause the video and try to figure out whether it's removable or non-removable discontinuity. Yeah, so I hope you've done it, and yeah, so, and of course why, right? So it's actually non-removable. And the reason is that if you look at limit with x approaching, let's say that pi over 2, right, from the left, so that's minus, right, so that equals, so let's look at it, right, pi over 2, and we're approaching pi over 2 from the left, right, so from this way, right, so the values of the functions are going towards positive infinity, and then we're checking whether that is equal, right, whether this works, and we have a limit with x approaching pi over 2 from the right side. So let's see what that equals. So when I'm going with my axis towards pi over 2 from the right, so you see that the values are going down, right? So that's not that should have been what, minus, right, negative infinity. So this one is positive infinity. Yeah, is that right? I don't think it's right. Let me look at it again. I know they're different. Let's see. So this one, pi over 2 from the left, positive infinity, okay. Pi over 2 from the right, negative infinity. Okay, so there should be minus here. Yeah, so non-removable because the limits are not the same. Okay. Yeah, so let's look at a couple other functions that are kind of typical. So example 7. We've seen this one. F of x equals sine x over x. Okay, so we know that the limit is equal to 1. So limit with x approaching 0 is 1. Let's put that function there, yeah. Hold on. What do I need? Okay, so this is sine x over x equals 1. Yeah, so this one is discontinuous. Let me show you the graph, remind you what the graph looked like. Okay, so this is, let's say this is 1. And the function, the graph looked something like this. So this is an open circle, and the function looked like this, right? The amplitude decreases the farther I get from that y-axis. Anyway, they're supposed to be symmetrical. Yeah, so the function is And now again, right, is this removable or non-removable? Well, it's removable because, right, the limit x approaching 0 from the left of f of x, right, it's the same as limit so limit with x approaching 0 from the right of f of x. Okay, so it's removable. Okay, next example. It's example 8. This one, this is strange. You should graph this one using some kind of device, Desmos. So sine of 1 over x. Yeah, so this one, and if you graph it properly, I'm not graphing it properly, but basically what's happening, right? So the closer I get to 0, right, the more oscillations I have, right? So the closer I get to 0, the faster the function, the graph goes up and down, right? So then here on this side is, right, symmetrical. Okay. Right, so this one, this function is not discontinuous. Even though, right, there's no obvious break, right, in the function, but it's still discontinuous. And it's not discontinuous, it's not removable. There's no limit, right, at 0. The limit doesn't exist. And non-removable. Okay, so these are two pretty typical, right, examples of that discontinuity of those two functions that are discontinuous. Now example 9. Okay, this one is basically very similar to the previous one, but it has an additional variable x in front of that sign. So it's 1 over x. And yeah, so the function, let's look at the graph. The graph is interesting. Again, you should graph it properly. Okay, so we have two let me see. Yeah, so we have absolute value of x, right? And that's a continuous function. And there is another graph. This will be y equals negative absolute value of x. This one is y equals absolute value of x. And our function, okay, let me make it green. It's not easy to graph, okay, but that function is between those two graphs, okay, so it kind of oscillates between those two graphs. Now, of course, we're checking whether it's continuous at 0, right? So then this is not nice. It should go down, and this one should go up. Anyway, they should be symmetrical. Well, it's not, but anyway, so the function is right. We're checking at c equals 0, obviously, right? Because at other x's the function is continuous. Okay, so it's discontinuous. Okay, and it's actually a removable discontinuity. Okay, yeah, let me just mention squeeze theorem. Maybe we'll look at it later. Um, so this one, that the fact that it's removable. Okay, let me make it. Right, so we need to basically show that the limit, right, going from the left and going from the right is the same. So the fact that the function is removable, it's proved by the squeeze theorem. And it goes, let me make it. Let me actually write it. So the function, I mean, that's not this theorem, but it's just a conclusion for it. Y equals x sine of 1 over x is squeezed between two other functions. Their limit is the same, is 0. Therefore, the limit of f of x must also be 0. Okay. Yeah, so don't have any other examples. Let's do a couple other problems. Let's do. Oh, actually, I do have I have another example. It's just of that problem I was mentioning. So this is, I don't know. Let's call it example 10. So let f of x equal and another piecewise function. So it's 3x squared. If x is greater or equal than 1. And then here we have ax minus 4 if x is less than 1. Okay, so what we need to do is find a so that, or such that the function is continuous. Is continuous. Okay, so again, right, the only point of discontinuity could be this, right, because both of those functions, 3x squared and this is just a linear function, are continuous. So yeah, let me draw the situation, right? So we have the parabola. It's this one. Or actually, let me make it dashed, right? Because we need to keep only the part of the graph for x is bigger than 1. Okay, so we keep the section of the parabola for x is bigger than 1. So 1 is here, and so this branch. And we can erase the other part. And so we don't need this. Okay. Yeah, so that's the parabola, and then the other function, and I don't know, something like this. Okay, so you see that the point of discontinuity can only be here. So we need to find the a so that there is no point of discontinuity, right? So that the function kind of, so that basically they touch right there, right? For x equals 1. So because they need to touch right there, the y, right, needs to be the same for both of the functions. For that, x equals 1. Okay, so should we write it? Let's not write it. Let's just write. Right, so I'm going to take the first function. Right? So 3x squared. And then y equals ax minus 4. So y needs to be equal to y at x equals 1. Okay. Yeah, so let's take the first function. So 3x squared needs to be equal to ax minus 4. And we plug in that 1 in for x. And we get 3 times 1 squared equals a times 1 minus 4. Okay, so we get 3 equals a minus 4. Okay, so looks like a equals 7, not 4. 7. Okay, so the function is continuous if a equals 7. Alright, so that if we want to, maybe let's write that that continuous function with that 7 in it. Okay, so we have f of x equals 3x squared. I forgot it's a piecewise function. Okay, so 3x squared. If x is greater or equal than 1. And then we have that 7x minus 4 for x is less than 1. Okay, yeah, let me give you a couple of problems to practice. Okay, so the first one is, and we'll discuss the continuity. All right, so again, the piecewise function. Right, so when you have those piecewise functions, what do you need to do? You need to check continuity at those junctures, right? So in this case, it's going to be 1. Right? That's the first juncture. The second function is x squared plus 4. And then the interval here is x is between 1 and 2. So this needs to be x. And then the third function is x cubed, and x is greater or equal than 2. Right, so we have those two, right? Two values for x that are suspicious. So you just need to check, right? So the first point where the function can be discontinuous, or first number, first x, is that 1. Right, so 1 is part of this function. Well, not really, but, and also this function, this function. Right, so you need to check whether the, right, for x equals 1, whether those two functions have the same y. Okay, and then check the same for that number 2, right, between these two functions. Okay, so we don't need to go through this definition with 3 different conditions, right? Because all 3 functions, right, this one, and this one, are continuous. The only problem is those 2 junctures. Okay, so I hope you understand what you need to do. I'll give you an answer. I'll give you answers in a moment. Okay, then the second problem is that problem that you need to find c, right? And again, or find that coefficient for the function to be continuous. Okay, so we have the first one is cx plus 3. X is less than 2. And 3x plus c. And x is greater than 2. Right, so find c so that this function is continuous. And the last one, well, let me give you let's write the last one. So problem number 3. And again, right, you need to find the coefficients. So, and the function looks like this: f of x so we have ax plus 5 for x less than 1. Then we have x squared minus bx plus 9. And I hope I can fit it here. Hold on. Yeah. So that second interval is from x is between 1 and 4. And the last function is ax squared minus bx minus 7. Okay, and the interval here is x is greater or equal than 4. Right, so you need to find those 3 coefficients. There's a, b, and there's no c, I guess. But you have those 2 coefficients here. Okay. Yeah, so let me give you answers. So the first one is discontinuous at 1. Let's put that c there, actually. At c equals 1. Okay, and continues at c equals 2. Okay, that's second problem. Let me see. The answer is c equals right. So you understand that this c is different, right? So that c, this c. Let me grab that. Right, so that these 2 c's are in a sense, right, the c's that we were using in the definition, and this c is just the coefficient, right? This coefficient and this coefficient. Okay. All right, and then the last. So maybe we should put x there. It doesn't matter. I hope you know what's going on. Okay, the last problem, a is equal to 2 and b is 3. Okay. Yeah, so that's it. That's the end of that section.